Hello. So today we are doing this problem called word search. It's a medium level problem, and the problem states that we are given a board, a 2D board, and let me just try to. How can I? Yeah. So we get a board, a 2D board, and we want to find if the word exists in the grid. And the word can be constructed from letters of sequentially adjacent cells, where adjacent cells are those that are horizontally or vertically neighboring. So we need to consider only horizontal or vertical neighbors. And the same letter cell may not be used more than once. So the same letter, we should not go and then go back to it and use it again. So this is very important. And then we get, so basically we get the board and we get the words. So for example, A, B, C, C, E, D. You can go this way, but that won't yield anything but we can go A, B, C, and then go down to this C here. After that, go down to this E, and then go left to this D. That will give us the word. And for C, we could go to this S. This S won't give us anything because there is no neighboring E, but this S will give us this E, and then we can go left to get this E. For A, B, C, B, there is no way, because when we reach this C here, there is no B, adjacent B, and then there is no other A, B that we can go to. So we return false. So you can see what I did here when even doing it manually. It was starting from a character that is in the board that matches the start of the word, and then every time keep going, checking for one that matches the next character in the word, in the next one of the neighbors of the letter I'm at in the board. And then if I reach the end of the word and I have found each letter until the end, then I can return true. If I didn't, and I can try, for example, here, there is no S, there is no E, so I can look at the rest of the board and find another S and start looking from there. So exactly this, what I'm doing here is DFS, because I'm starting and I'm going as much as I can down until I reach either the end or I don't reach anything. Then I pick up another point of the board or another letter in the board. So that's basically what DFS is. And so let's just write this as a DFS solution. So what we need is, what we did here manually was to go through each letter of the board. So let me just write this like that. And we have this as the word. So what we want is to go through try to find each start of A. So we want to find the start of the word, basically, which is A here. And so we need to go through the board. So let's just say in I and row, I can enumerate the board. And we can go for G, and the value is in enumerate of row. And we can check if the value is the same as the start of the word, which is A here, which we can find here and here, for example. Then I start doing my DFS traversal. So I can find something, for example, for this, so I can find this occurrence here. And so the way I'm going to do that is just I'm going to call DFS and with the positions and with the index of the start of the word, so that every time I go down, I can keep track of at which index I'm at in the word, so I can know with which character in the word to compare which character in the board, basically. And so we do that, and if this gives us true, that means we found an occurrence of the word, and that's basically all we are asked. And so we can return true. So now, if we go through all the board and all the letters that match this and that match the start of the word, and try to find the word, and we didn't find anything, then we can just return false. So now let's write the DFS function. So DFS has I, J, K. And so we can, so one thing is we need to go through the neighbors to find, for example, here for this B, we need to go through the neighbors of A to find B. And the neighbors are just the adjacent values horizontally and vertically. And so to find these are just, so we can just go through them like this, neighbor I and neighbor J in. So it's I plus 1 J, it's, which is this one, the right neighbor. We can look at the left neighbor. We can, sorry, it's the, this is the down neighbor, this is the up neighbor, and this is the left neighbor or the right neighbor, and this is the left neighbor. And so we go through all of them and we check if we find DFS. So we do the DFS also on that so that we can go to the next. We can go until the end of the word. So so at B, for example, we found B. So we go also to find C. And so in order to say we want to find C, we can just pass to the Dfs function. We can pass index. Let's call this index instead. We can pass index plus 1. If this one goes all the way down and finds the word, then we can just return true. However, if we go through all neighbors and we didn't find the rest of the word, then we can just return false. Now, when did we say, okay, stop, we found the word? That's basically when we reach the end of the word and we didn't return false because of a boundary check or because the value that we found at a position is not equal to the value at the board. So here, if the word index, if actually the index is the length of the word, then we can just return true. Now, what are the conditions that are not valid? So if board at ij is different than the word at index, which means if the character say C here, and for example, let's say if we go down to F, if F is different than C, then we don't need to continue. We will not find the word from there, so we can just return false right away. And also, we want to check the boundaries that we didn't go past them. So for that, we want to check. So if it's not within the boundaries, which are for I, it needs to be between length of board, and for J, it needs to be between J and length of board of I. And we need this. There is one other check. So the problem stated that here that the same letter cell should not be used more than once. So we should not go visit it again. So at this point, we have two ways to handle this. We can handle it either by creating a visited array and keeping the value, or like a visited Boolean array, and keep, if when we visit a value, we can set it to true. And when we exit that DFS search, we can set it to false. Or we can do a simpler solution, which just change the board temporarily so that the board IJ here wouldn't match the word index. And so if it's the same letter we will that we used before, it will return false. And so we could just say save the original letter here and set the board to be just anything, let's say none, or let's say this star character. And once we finish visiting all the neighbors, which means we will not use the word, the letter again, at that point we can just put back the value. And this should be enough. Yep, let's try to run this. Yep, so it's enough and that. Did we check? So if not, So somehow our check here is not, oh, actually it's or. So either this is not valid, it's not a boundary value, or it doesn't match the word letter. Okay, schema this. Okay, so that passes. There is a cool trick that we can do here, a cool optimization that makes the code shorter. So the way we are going to do that is using Python has this thing called complex numbers, where you could have 1 plus 2j, and then 1 plus 3j, and things like that. Right, and you can do operation on them. For example, you can add 2 to this, which will give you 4 plus 1j. You could do 2 plus j minus 1j minus 1j, or minus 2j, which will give us a value minus j. So we can transform our board, which currently just uses 0, 0, and for example, 0, 0 can have the value a at 0, 0. For example, here, if we take this board, 0, 0 has the value a, right? And so instead of mapping it to I and j, we can just map it to one value, which is 0 plus 0j. And for example, for f here, which is 1, 1, at 1, 1, we have f, value f. So we can map this to be 1j. So basically, this allows us to, instead of have two indexes to reference a value in the board, we can just have just one index that is a complex value. And so the way we can do that is we can just say the board now is going to be equal to I. That's what we did here. We did I plus j. So this is basically is I plus j multiplied by 1j. And so this j here is for the complex value. So we have multiplied by 1j, and we map that to the value. And what are these? So I is just the index of the rows. So we can enumerate the board to get that. And j is just the column. So, and this will get the value here. And that's what we put here. And so we'll do enumerate row. So this trick actually can be used to simplify access to any grid or any matrix. And so once we have this, we need to do DFS on all values, right? So that we can check each start that we haven't checked yet. And so, and our goal, whenever we find a DFS that finds the word, we need to just return that and stop. And so we can use Python's any, which just keeps iterating. The first time it finds a truthful value, it exits, and that's what we want. And so we'll do DFS on Z and the index of the start of the word. So remember, before we did DFS on IJ, but since now we can reference each value by just this key, so we need just that key, which is Z. And what is Z? Z is just the keys in board. And so we can just say for Z in board, right? And so we need to define our DFS this time. And our DFS now takes just Z instead of IJ, and takes index for the index of the word. And then now we can do the same thing that we did earlier. So we check if the index is equal to the length of the word. That means we found an occurrence of that word, and so we can return true right away. And we can check the boundaries, but using this simplifies checking the boundary a lot, because now we don't need actually to check the boundaries. We can just say if board.getZ is equal to word index. We don't need to do the check for boundaries, because if the value is not in board, then which is the case for values that are outside the bounds, then this value would just be none, right? That value would just be none, and none is different than the character at the word index, definitely. And so this here would not work. So if we say different, then that's equivalent to both checking the bounds and checking that the character matches, because it's none if the character is, if Z is not in board. And so, and that's the case for indexes that are outside the boundaries. So this simplifies our check for out of boundaries, because now we just need to do this. And we can return. So if that's the case, we can just return false. And now we can do the same thing we did earlier, so that we can keep track of the board value. And then this is just so that we don't use the same letter in the board twice. So let's just say none here, so that it doesn't match this. And this actually, we can write it in a shorter version, so we can just say board Z, and we can say none here instead. And now we can go through the neighbors of the board. And to go through the neighbors of each of this Z is even simpler with these complex values. So there is a property for complex values that is interesting, which is, so we know j to the power of 1 is just j, right? But for complex j to the power of 2 is actually -1. And j to the power of 3, that's actually minus j, because that's like j to the power of 2 multiplied by j, which is minus j. And j to the power of 4 is just 1. And j to the power of 0, that's also equal to 1. So given these properties here, we can do something interesting, which is, so if we have a value, let's say we have this position 1. What are the position 1, 1? What are the neighbors? The neighbors are 0, 1, up, and then down we have 2, 1. And then here we have the position 1, 2. And then here we have, position we have here is 1, 0, right? And so given that we know this, so let's see, how can we obtain these values so we want to find the neighbors of this 1, 1, right? So the neighbors of this one, you can see if we do, so that's in our new indexing system, 1, 1, 1 is just 1 plus 1j, right? J multiplied by 1j. Now, if we do 1 plus j multiplied by 1j, which is the index, and add j to the power of 0, that just gives us 2 plus j multiplied by 1j, right? Which is actually the position, 2, 1, right? And then if we take also and add j to the power of 1, that gives us 1 plus 2j, right? So this is 1 actually. Just to not confuse you. This is 1, this is 1. So if we add j to the power of 1, that will give us 1 plus 2j. So that's like 1, 2. Now if we add j to the power of 2, that's 1. So that's basically 1 plus 1 multiplied by 1j. And since j to the power of 2 is -1, that gives us 0 plus 1 multiplied by 1j. And this is exactly, so this is I and this is j. So that's 0, 1. And if we take j to the power of 3 here, we can have 1 multiplied by j. And what is j to the power of 3? That's like minus j, right? So that's minus j. So this is j minus j. That gives us 1 plus 0, j, right? And so the value here is 1, 0. So you can see we ended up finding, by adding j to the power of 0 and j to the power of 1 and j to the power of 2 and j to the power of 3, we ended up finding 2, 1, which is this one, and 1, 2, which is this one, and 0, 1, which is this one, and 1, 0, which is 1, 0 here. So we ended up finding all the neighbors. So in order to go from x plus yj, we can just multiply by j to the power of k for k in the range in basically 0, 1, 2, 3. So basically 0, 1, 2, 3. So this is the range of 4, right? So we can just, to get the neighbors, instead of doing all the positions, we can just multiply by j to the power of k for k in the range of 4. And so that's enough in visiting all the neighbors. So we can do here DFS. To get a DFS for neighbors, we can do DFS on z, which is this value here, multiplied by j to the power of k, which in Python we can write that plus, actually. So we did a plus. That's what we did here. We did plus. And so plus j to the power of k for k in range 4. And this will do DFS on all neighbors. And so what we want is, if any of them returns a true, then we found an occurrence of the word, and so we can just return true. Otherwise, we can put back the value of board z to the original value so that it can get considered, and then we can return false at the end. And you can see this method is a lot shorter. At first it looks complicated, but once you understand this here with using complex values to visit neighbors and taking advantage of the fact that when we get the key and it doesn't exist, then it returns none, so it would be different. And so we don't need to check the boundaries. And that's all there is to it. It becomes very simple to do. Yeah, so let's run this and see if it passes. So we are missing, so we want DFS to go and do index +1 for the word too, as we did before. Okay, we're missing something for this, so yeah, to make it a complex in Python, we need to do 1j. Let's just make this. So we still have a problem in the generator here. Yep, so actually we need to first call the function, and then outside of it we need to do the for, so that it can run for each value of k. Okay, so that passes. Let's submit this. Yeah, okay, so that's successful. Yeah, and that's this trick to keep in mind to simplify the access to the board and simplify the logic here. Yeah, that's it for now. See you next time. Bye.